All right, hello, greetings. So for your Chapter 10 homework, you're asked to solve exercise 10.1 through 10.5, which is essentially one big problem. So in 10.1, we're going to start with our Lotka-Volterra model. So for modeling an ecosystem, and we're looking at the dynamics of our rabbit and fox population. And so we're going to start on 10.1. We'll solve our Lotka-Volterra problem, and I'll do this in a second. And then within this video, I'll also look at 10.2. So 10.2 is just going to be, once we have our solution, to play around with the effect of some of the parameters. And then we'll continue to build up our Lotka-Volterra model by improving the growth rate part of the Lotka-Volterra model for rabbits. Okay, so let's jump in and do it, and we'll do this in a series of videos. Okay, so in exercise 10.1, we have our Lotka-Volterra model. So here, R prime, right, indicates dr dt, F prime is df dt. So this is the rate of change of rabbits, and this is the rate of change of foxes in my system. And so key is, when I look at my rabbit term, is I have this first term, A times R. So this is our kind of conventional or traditional exponential growth term. And so in the absence of foxes, right, the population of rabbits is going to grow exponentially. So the rate of change of rabbits is proportional to the current population of rabbits. Okay. Just like if I look at my fox term, in the absence of rabbits, then we have an exponential decay, right? So df dt, the rate of change of foxes is proportional to the current population of foxes, and it's negative because it's a decay term. Okay, when I say exponential growth, exponential decay, that's just if I were to solve that differential equation in isolation, which we'll actually do in 10.3. Okay, but then my rabbits are also going to be consumed by foxes, so I have my growth term, but then I have a consumption term, which is proportional to the current population of rabbits and foxes. It's negative because it's a decay term. Okay, then I have this term, and then I just multiply by an additional constant, so it's the rate of change of foxes is proportional to that term, okay, but it's positive because foxes are growing, right? They're the ones doing the consuming of the rabbits. Okay. And then within the problem, we're given some parameters, we're given initial conditions, and I give us a reference point. If we were to solve over the course of 365 days, here's what I get at 365 days. Okay, and in this problem set, we're more interested in looking at the graphs and getting qualitative results. So just kind of as a difference. So if I jump over to MATLAB, so if I'm going to start with 10.1, okay, to solve, I'm going to start by generating a new script. And my first step to solving my differential equation is I'm going to generate my rate function. So my rate function can have a single input and it's going to have a single output. And it's going to have two inputs. First input is going to be my independent variable t. Second input is actually going to be a vector containing values of my dependent variable at that value of t. Okay, so I'm going to have function res, and I'll call this Lotka-Volterra, and it's going to have an input of t, and then I just tend to use this generic variable m to indicate my matrix or vector that's going to contain the values of my dependent variable. Okay. So then the first thing I tend to do is I like to do what I call unpacking m, right? So m is going to be a vector containing the values of our dependent variables. So in this case, we have two dependent variables, r and f. So ODE 45 requires that we have a rate function with two inputs, okay, even though we have more than one dependent variable. So how we condense those multiple variables to one, right, is by packing it into a vector. So I like to start by unpacking, and so let me type it up so you can see what I mean by unpacking. And so what I mean by unpacking is I'm going to create a new variable r, okay, and r is just going to be the first element of m, and then we create a new variable f corresponding to population of foxes, which is the second element. Okay, so this is rabbits, okay, and this is foxes. Okay, I think it's an ES. Oh, but that's a good question. All right. So the general idea by unpacking is I could just use this matrix M and refer to the elements of that matrix when I write my rate expressions and such. Okay. But I like to unpack. This way, when I write my rate expressions, I can write them in a form more similar to what my actual differential equation looks like is 1. And then 2, it's going to help me keep track of my order, because the order of my dependent variables here, right, first is R, then is F, is going to be the same order of my rates, which are going to be output in res. So when I res, the first element's going to correspond to dr dt, and the second one's going to be df dt, right? And so that order is going to be consistent. That order is going to be consistent when I define my initial conditions. That order is going to be consistent when I look at my output matrix containing my dependent variables a function of time. First column will be R, second will be F. So it just helps me keep track of everything. Okay. So next I'm going to define my parameters. Okay. And so we have A, B, C, and E. Okay, so A is 0.1. B is 0.01. C's 0.1. And E is 0.2. Okay, and then next I'll compute my rates. Okay, and I'm going to write out separate lines for each rate. I'm going to assign those to variables so that they look like my differential equations as I have them written, and then I'll pack them up to return them. Okay, that's just me and my style in doing so. Okay, and so what I mean by that, right, I'm going to have one rate which is dr dt, and I'm going to assign that to variable dr dt, which looks just like my differential equation, and I'll have a second one which is df dt. Okay, so if I first look, dr dt is equal to A times R minus B times RF. So it's equal to A times R minus B times R times F. Okay, and I'm just going to update these to use element-wise operations. Okay, cool. So by unpacking, now when I write my differential equation, right, my differential equation looks very similar to what I have right in my problem statement. So df dt is E times B times R times F minus C times F. Okay, and I'm just going to update these to use element-wise operations. Okay, great. The last step is going to be pack and return. Okay, so I need to return my rates, and so my output variable that I have is my generic variable res, and you could call this something else. You could call it like dmdt, whatever you want. Okay, but key is going to be when I pack up and return my rates is that res needs to be a column vector. Okay, so m, right, is some input that's being passed to my rate function. Okay, but that vector that gets returned, my vector of rates, needs to be a column vector. Okay, and so when I pack them up, the first element of res is going to be dr dt. Column vector, right, means separating the elements via semicolon. So dr dt, then df dt. Bam. There is my rate function. I'm going to call it Lotka-Volterra m. Perfect. All right. So then it's a matter of, well, what do we want to do, right? We can make a script to call this animal. We can make a new top function. All the same. Okay. What I'll do is I'll create a new top function just because that's often how I like to roll. So I'm going to create some new function, and actually it's going to have no outputs. And I'll call it Lotka-Volterra, and I'll call it 10.1. 10.1. Okay. Okay, and so I'm going to do save as, and I'm going to call this Lotka-Volterra 10.1. Okay, and then that way I still have my rate function here, right, which I can put up in share. Okay, so this is going to be solving and plotting my fox and rabbit population over the course of 1 year. Okay. Now when I solve it, if I just had an ODE 45 call, it would generate a plot. But what I'm going to do is, just so you can see me interacting more with the data, is I'll save the results to variables and then plot. And also, to make this more clear, let me start by creating variables for my initial and final time. Okay, so T naught, right, is always going to be essentially 0. Okay, and then T final in this case is we're solving for the course of 1 year. Okay, and we're given a reference value of 365 days. Okay, so the parameters here are based on assuming a unit of time of 365. Okay, so T finals could be T65. And now I need my initial conditions to solve. So in terms of initial conditions, we're given initial rabbit and fox population here. Okay, so I'm going to call these R naught is equal to 100, and I think it was F naught was equal to 10. Yeah. All right, so now I have my time range, I have my initial conditions, so I'm all ready to solve. The one note I wanted to remind you of before I do solve is when I look at my rate function down here, t is underlined. So basically I have this input variable that isn't used anywhere within the function, is what MATLAB's telling me. So what we have going on here is I'm going to solve my differential equation using ODE45. ODE45 requires a rate function with two input variables, right? First being my independent variable, second being my dependent variable. Reason being is my rate could be a function of both my independent and dependent variables. Okay, in this case it's not, right? So it's not used. But you still need to have that first argument there, because that first argument is where my independent variable would go. What MATLAB's suggesting is what would be better is to use a tilde. Tilde is essentially just a placeholder. I have a tendency to use t though regardless. Just this way, whenever I write a rate function, my rate functions look exactly the same, and then I really burn into my head that this first element is my independent variable t. Okay. So back up here though, so now I have my time range, my initial conditions, so I'm going to solve. Now if I were just to call ODE45, it would generate a plot, which is what we're going for. I'm going to save the results to variables just so you can see me saving to variables and manipulating it, and then we'll go from there. Okay, and actually maybe let me build it up, right? So if I were to just start with ODE45, okay, first argument's my rate function, which in this case is Lotka-Volterra. Second's going to be my time interval to solve over, so it's going to go from T naught to T final, right? And I store these to variables. One, if I want to update, it makes it easier. But then hopefully once you see this command too, it'll make more sense as you're practicing here. Okay, so first argument rate, second argument time range, third argument's my initial conditions, okay, which in this case is going to be R naught and F naught. Okay, here I could just use a comma to separate the elements like a row vector. Okay, but down here, right, it's got to be a column vector. Now, if I just call ODE45 in this way, okay, and actually what this is, I spelled it differently. Let's see, now are they spelled the same? Lotka-Volterra. Oh, so this is saying that looks like I spelled it wrong, differently. L-O-T, oh, I did. Spelled the Lotka part right. Okay, all right. Cool, so now I've spelled that correctly. So if I just call ODE45, okay, I have a function with no input, so I can just run. Okay, the result's going to be a plot, right? And it'll just generate the plot. And I could add labels and do everything there, and that's good and fine. Okay. The other way I can run this, okay, and what we typically do is we're typically interested in the actual data besides just the plot. And so ODE45 is a function with multiple optional output variables. Okay, and so I assign the output. I'm going to use this bracket notation to get my variables. Okay, and remember here, right, first in my rate function, first came my independent variable, then my dependent variable. That's how it works in terms of output as well. First output variable that I can pull back is my, it's going to be a vector of my independent variables, t, and then I'll get a matrix of my dependent variable, which I'm going to store for m. And so I'm going to run it, and we'll look at m, and I'll point out exactly what it is, and we'll go from there. Okay, and actually, this is where I guess I have a problem, because I have a So I'm going to return M, right, just so I can pull it up here in my command window and you can see exactly what it is. Okay. All right, and so M, right, is 185 by 2. Okay, so it's a matrix, and first column is going to correspond to a column vector essentially of dependent variable 1. Okay, and then this is column vector corresponding to dependent variable 2. And so this is where I like unpacking. Oop, stretching my head out as I try and move it, because then I remember column 1, right, is R, column 2 is F. Okay, just like this order is RF, okay, RF, okay, RF. And so why I do that is I could work with and plot the matrix, but I also often like to chop it up, and it's something students often find advantageous, so that's easier to keep track of. And so I can say, something like splitting up M into its components. Okay, and so if I wanted, let's see, first column is R. Okay, so R, my rabbits, would be, I'd be looking at vector M or matrix M. Okay, and it's column 1. So I want all rows of the first column. So my shortcut for all rows is just colon, and then first column would be 1. Okay, foxes. Okay, I again want all rows. Now the second column. Oh. Okay, and now if I want to, now I can generate my own plot. And so maybe I open up figure 1. Okay, I'll execute a hold on, and I'm going to plot first R versus T, and maybe I'll make that a black line, and I'll plot F versus T, and I'll make that a red line. I'll add an X label, and that's going to be time in days. I'll have a Y label, and that's going to be population. And I'll add a legend, and that legend is going to be first is rabbits, and then second come foxes. Okay. And I should mention right before I even do anything, okay, since I see the output here from when I just ran for 365 days. Okay, remember when I look at M, so if I were to look at the T vector, first element of my T vector is T naught, last element's T final. In between, I don't know exactly what times I'm going to get because MATLAB's choosing essentially delta T on the fly to achieve a given level of accuracy. Okay, when I look at my M vector, okay, first row is going to correspond to, first row is going to correspond to values of my dependent variable at T naught, okay, which should be the same as our initial conditions. Okay, so I could match up the elements of M with the elements of T to figure out what time that corresponds to. But the only other value I know is exactly going to be there is, we said the last element of my T vector is T final. And so if I wanted to know the values at T final, right, that's this. Right? In general, that was a trick we used in class. If I wanted something more like an analytic function, I would create a function that solved my diffie from 0 to t, where t was my input variable. Then it'd return the value of my dependent variable at t, right, which is more in line with an independent, with an analytic solution, where if you specify t, you get the value of your dependent variable at that time t. Okay, but before I do that, right, just as a check, right, these should be the reference values we were given, right, 22.6552 and 6.7519, right? So the values I'm getting here, the same values were given in the problem as kind of our reference values. So yeah, so I'm going to delete this since I'm just interested in the plot. So now I run it, okay, and now I have this plot. I have population versus time in days, blacks, rabbits, and then red is foxes. Okay, and we could think more about this, but I'm just going to leave this. Okay, and then just to comment on the second problem while I have this up, is the second problem is just kind of qualitative. It's just asking you to look at the effect of A and looking at the effect of C. All right, so A is the growth rate of rabbits. All right, so the question is, what would happen if the growth rate of rabbits were to double? All right, what would change? Um, well, how could I do this? Well, one, if I just wanted to make a side-by-side comparison, okay, maybe let me do so this is 10.1, okay, I'm going to do a save as, I'm going to save this as 10.2, okay, and what I'm going to do in 10.2, okay, is I'm going to create a new figure, figure 2, and then down here, we said let's double A, alright, so let's make A 0.2. Okay, so if I run it, and if I just double the growth rate of rabbits, keeping everything else constant, right, what happens? Here's what I get. And you kind of get this, interesting change in dynamics in which it does look like the peak height changes. So before, my max population of rabbits was about 100. Now it's up about 130. Okay, but then also, so the kind of amplitude, right, goes up, but it looks like the period actually, decreases. We get these, quicker oscillations within our populations. And so I guess there's more, and so there's more rabbits for foxes to consume, right, and they're quickly changing. The max population of rabbit or foxes also goes up. Before we were about 20, now it doubles, it's about 40. So it looks like the max amount of rabbits goes up, max amount of foxes goes up, and then the period goes down, right? So 1, 2, 3, 4, 5, 6 peaks before. Now we have 8. Okay, cool. And I think 10.2 also asks about putting A back to its original value and then changing the death rate of foxes. All right, and you could play games with that as well, doing a similar trick. Okay, but kind of the idea is once you have this model set up, it kind of becomes fun in that you can play around with the parameters and look at what the effect is. All right, and that would also be if I'm actually trying to model an ecosystem. I could come up with this Lotka-Volterra model based on physical intuition in terms of what I expect for the rate of change of my populations in my system, right? I could solve it, and then essentially I could tune my parameters so that my model fits some experimental data or actual data that I'm collecting. Okay. So yeah, so you'd keep playing with 10.2, but hopefully that gives you a good idea and gives you enough to solve. Let me know if you have any questions.